Well, welcome everyone to the, oh, I've lost count, the second in our seminar series for 2016. Our guest is Dr. Arild Hestvik from the Department of Linguistics and Cognitive Science at the University of Delaware. I've known Arild for longer than we both care to remember. We were sort of grad school at the same time. But this is the first time he's been up here to Newfoundland. He's a specialist in the use of brain toys to discover how language fits in the brain. And he's graciously agreed to come tell us about what that tells us about underspecification. So, Arild?
Thank you very much, and thank you very much for having me here. It's quite a pleasure to come to this remote island. More remote than I actually realized. And I'm from Norway, and this looks just like home to me, actually. The weather, everything. So I'm going to try to tell you a long story. So it's quite a big talk, and I will not overwhelm you. I'm going to try to find the right amount of detail and time to spend all different parts of it. I know probably more about the brain side than the phonological side, the specification side. So please arrest me if I say something that's not accurate. Also, this is work that I've done in collaboration with a phonologist, Karthik Durvasula, who was a PhD student at the University of Delaware and is now at Michigan State University. So this is very much collaborative work. So he actually came up with the predictions for phonology, and I had the experimental methodology together, and something came out of it. So let me get started. So here's my battle plan. We're talking about battles all day, so it's appropriate. So I'm going to try to first spend a little time giving a background. I'm going to talk about the difference between phonetics and phonology, and I'll try to introduce the idea of underspecification, and then pose the question that I'm seeking an answer to. And the answer comes from measuring something inside the brain. So in order to, so I like to try to explain a little bit about the measure too, so we can see where this data really come from, rather than just showing you some fancy pictures. It's always more interesting to know where the measure comes from. So I'm going to try to explain that, and once I've explained all that, I'll then go through the experiments where which we ran to test some predictions about underspecification that we have for brain data. And that's the plan. So let's go. So first, so the first thing, here's the background thing, right? So we all know. So what's the difference between phonetics and phonology? I remember having posed that question to myself and to my undergraduates in 101 many times, right? So you want to teach the students what the phonetic transcription, right? And then you also want to explain the concept of phoneme. And it's actually not so easy to do sometimes. Or undergraduates sometimes have very difficulty understanding that difference. And maybe the reason the reason it's hard to understand is because we're not explaining it right. So here's my take on the best explanation of the difference between phonetics and phonology. So phonetics, when we're talking about phonetics, allophones and phones, what we're actually talking about is some physical events in time and space, right? So space is the area inside your mouth, and time is real time during speaking. So phonetics is about action. So if you want to do a phonetic description of some speech coming out of somebody's mouth, what you're trying to do is symbolize the actual physical, acoustic, articulatory events happening. Right? So that's phonetics. So I remember when I was teaching Ling 101 in Norway, we always have to have the students, they have to learn to do very close phonetic transcriptions of their own Norwegian dialects. Right? So in Norway there's lots of different dialects, so we have to make sure that one way of testing whether they actually knew phonetics was to find out, okay, what's the dialect you're speaking? Is it from this valley or down south, and we knew how they spoke, and then we checked their phonetic transcription time to see how close, how accurate that was. So for instance, there's many ways you can say T. You can say a T with aspiration, or you can say a T without aspiration. You can say a T with stress or gemination. So every speech sound can be produced in lots of different ways. Speaker, everything, right? So phonetics is about describing that aspect of speech. Phonemes, on the other hand, are not descriptions of things in real time and space. Phonemes are descriptions of an abstract mechanism for storing a specific aspect of speech sound that serves the purpose of differentiating all the words you have in memory from each other. So a phoneme is sort of like a static long-term abstract mental entity, versus phonetics is about the real-time events of the physics and acoustics of speech. So that's one way. So try to make those two things as different as possible. This is not a view that's shared by everybody in linguistics. So, for example, many of my colleagues kind of denying the idea that the phoneme is very, very special or abstract. They can describe it as, say, the sum of all the actual allophones, for example. Okay, like an equivalence. That's the phoneme. That's not the view of phoneme that I'm interested in here. That I'm talking about. So I like to sort of make the phoneme mental and static, and phonetics is something happening in time space. Okay, great. So the phones is what we produce when we're speaking, or what we perceive in a given time and place. The phoneme is some kind of memory information that is related to those events. Right? So just to illustrate, so for example, from speech perception, what happens during speech perception is that a sound wave travels through the air, hits the air, and moves some hair cells differentially inside the cochlea. That generates some nerve impulses. That goes to your brain. Your brain performs some kind of spectral analysis and then generates a representation of the phonetic event. So when I transcribe some speech with phonetics, I'm kind of giving a full description of the speech sound from the sensory perspective. So during speech perception, that kind of phonetic analysis also must happen. So when you're listening to me speaking now, your brain is constantly trying to guess, representing the phonetic description of the sound. And as we know from, and this is what we teach our students, phonetic description can be done by listing all the phonetic features that characterize that sound. And those phonetic features will be exhaustive, right? So if there's some feature that we need to differentiate one T from another, we add that to the phonetic description. And we also do that when we listen to speech because we can understand, we do carry information about phonetic variability, for example. So I know that when I listen to my taxidermy speaking English, I can right away notice that there's something different about the phonetics of his speech that's different from Phillips English, for example. So we have to code, understand, and represent that too. But once we've done the phonetic sketch, what the brain is doing, we believe, what people like us, like couple and we believe that we then map that physical representation to an abstract representation, which is the phonemic representation. And very simply, the difference between a phonetic and a phonemic representation is that here we only use a smaller set of features, right? Here, once you enter into the lexicon, where you need to distinguish words from each other, you only need to list the distinctive features, the feature that has any kind of function in terms of distinction between words. So the phonemic representation has fewer features than the phonetic representation. So that is the main difference that I'm trying to focus on here. Here we have a very rich representation of features. Here we have a sparse representation of features. Alright, so when you hear a word and you first do the phonetic transcription, so to speak, and then you map that to a phonological representation, and what happens next? You take that phonological representation and you go into your lexicon to see if, okay, do I have a word that looks just like this? And if I have a word that looks like this, pull it up to your working memory, and then you establish, okay, I now recognize the word from the messy acoustic singlet came into my ear. So that's the picture of speech perception that I'm assuming. But the main thing to be focusing on here is the difference between phonetics and phonics, the difference in terms of feature richness. All right. So the question we'd like to ask them is, what is evidence that there is such a level of representation? And if you ask a linguist, they will give you lots of arguments for that based on phonological rules. So there's a whole set of sort of whole industry of argumentation based on linguistic argumentation, that there has to be a level like that. But if linguistic representations are, and they are, mental representations, it ought to be possible to find evidence for the difference between rich representation and sparse representation in the brain's memory system. So that's what we're going to do today. And in fact, I'm actually not primarily interested in the difference between this and this per se. I'm interested in some differences among phonemes in terms of how richly they're specified. And that's where underspecification comes in. So now let me just explain the idea of underspecification the way I understand it. So what's underspecification? Well, underspecification means that if you have a set of contrasts in the lexicon, say between different consonants, some of the features that you're using here will have a kind of default value. And if some phonemes have a default value for some of these features, you can simplify the representation by not even specifying them in the lexicon. So let me illustrate that idea with something else again. So we can already say that there's underspecification in many areas of linguistic knowledge. For example, you know you have a verb in your memory, right? So you know you have the verb walk. And you also know that you can say the same verb with past tense, walked. The question is, do I need to, when I know that I can say both walk and walked, do I memorize both those two forms? Yes, you could memorize them probably, but you also don't have to memorize them because you can produce the walked form by rule. Right? So one way, what many people think and believe is that when you're looking at your storage of words, you don't store everything that you can possibly say. You only store the things that you have to store, and then you can add some rules that will produce additional things. Right? So according to this view, you don't actually memorize past tense of walked. Maybe you do, but you don't have to memorize it. Maybe you memorize very, very frequent past tense forms, but you may not memorize the past tense of commambulate. I was commambulated. And that is kind of underspecification. You underspecify the past tense form of verbs. And the same would be true for other kind of flexional morphology like number. So the same argument can be made for feature matrices. So if you look at the set of phonemes you have, if there is one value of the feature that is less common, more marked, you can actually set up your system so that you don't have to specify the most common value, the most unmarked value. You can leave it unspecified, and you can say, I only need to make a value for my distinctive feature for those versions of the phoneme that are unmarked. Okay, phonologists have to chime in on this.
Not the other way around.
Not the other way around?
You specify what's marked.
Yeah, so you specify the value that's marked, but you don't specify the value that's unmarked. So if you do that, I don't know if you can make the same argument for phonemes that I'm just made for verbs, but maybe you guys can tell me. So is it true that the unspecified version of the phoneme is more frequent in words? Often. Okay. Thank God for that. So what you can do in your word representation is say, okay, I don't specify my unmarked feature value in the lexical representation. But when I want to produce the word, I have to put some feature value on it, right? Because the feature values are instructions to your motor system how to produce a sound. So then you can have a rule that says, well, I have a phoneme and it doesn't have a specification for a certain feature. Here's a rule that will fill in the most benign value in a sense, right? And then you get a specification. So if that's the case, then you will have words with a say phoneme, say voicing, for example. If the voiced or the unvoiced version of the phoneme is the unmarked value, you don't have to specify voice information in the lexical representation because it can be filled in by this default rule. Just like tense, right? So you can fill in default past tense rule. But if you have another past tense you want to express as something that's say irregular, then you have to call it in the lexicon. So what's the evidence? Let me illustrate this. Okay. So here's an evidence. Here's an example. So people have argued that when you look at the nasal sounds, so these nasal sounds are differentiated by where the tongue is making contact with the roof of the mouth. N, the tip of the tongue is behind the alveolar ridge. M, you have bilabial closure. And N, you have a velar closure. So there's three different places where you can put a closure, right, to make the sound. Apart from that, they're the same. They have the same features. So people have proposed that, in fact, the coronal place of articulation is the unmarked value, the default value for the nasals. So I actually don't have to specify any feature value for the place of articulation in a word that contains the nasal N. I have to specify any other version of the nasal that's different from coronal, right? So according to the specification, this is how the feature matrix looks like for N in any word that you're storing in memory. And the evidence, the linguistic type of evidence for that is that N assimilates very easily to neighboring consonants, right? So if I have the word 10 and it's followed by a B, then the place of articulation for the nasal actually takes on the place of articulation of the following consonant here. So we get 10 bangs, right? If you have 10 gates, the velar sound here actually exports its place of articulation through that nasal sound. So we get 10 gates when you're actually saying the word, right? And this one I thought of myself. I heard this in some John Wayne movie. But other words that ends with other nasals, like M, they don't assimilate. So if you have cream car, it's not pronounced cream car. It's pronounced cream car. Cream dress is not pronounced cream dress. It's pronounced cream dress. So the explanation for the difference between N and M with respect to assimilation is that this one will assimilate because it's in the feature matrix that comes to the sound. There is no place of articulation feature, right? So when you put another word in front and behind it, it's sort of promiscuous sound. Right? It takes on the place of articulation of the other sound. But because this M has a feature specification, it resists change. It resists assimilation. That's why you don't get assimilation. So M is specified as label place of articulation, but N is sort of open-minded. I can be anywhere. I can go anywhere. So this leads to a picture like this. So when you're looking at phonological representations, which is storage of word in long-term memory, say the word nose, the N here is really a feature matrix. It contains a manner of specification, but it doesn't contain a place of articulation specification in long-term memory. But if I want to pull this word out of my lexicon and pronounce it, I have to specify some place of articulation. Where's my tongue going to go? So then the rule comes in and says, well, just fill in the default value, which is coronal, and then you get N. So and it's important. So when you're thinking about phonemes, you have these partially filled in feature matrices. When you execute pronunciation, when you map that to the articulation system, you have to fill in a value for the feature. That's how you get a pronunciation. So that's the picture of underspecification. Personally, I have some questions about the motivation for logical motivation for underspecification. That's sort of something we can talk to the phonologist about. But does this match the? Is this fairly correct? Will I get an A if I wrote this in my phonology class? Okay. Okay. Now, so now I gave an argument. What was the argument I gave you? Right, was from a rule, right? From rule application. So the question I'm asking now: can we find evidence for this picture from other sources? Make sure I'm staying. Well, so so again, let's think about the difference between phonetics and phonemes. So phonetics, they only exist. That's a transient thing, right? They don't only exist in real time. The way I painted the picture here. Although we might argue that there's memory representation of phonetics as well. But the way I put it there, a phone only exists as an event, right? It's an ephemeral thing. It disappears once I pronounce it. But the phoneme is something that's part of your memory system, long-term memory system of words. So if that's true, and if sometimes phonemes have underspecified or partially filled in feature matrices, somewhere inside your head there should be some representation that corresponds to the feature matrix with some partial feature specification. So if it's in the head, can I measure it? Can I look inside the head to see if I can see that partially specified feature representation? And can I look inside the head and say, okay, here's a fully specified feature representation, here's a partially specified feature representation, and if I do an experiment, I can actually generate some data that reflects that difference. So that's the question that we're asking, that I'm asking today. Can look inside the mental world and see that. Now, so if you want to see that, you need to have some measurement that can, in a sense, look inside the head, right? So that's now where it's starting to get exciting, right? So how can you look inside the head? How can you get some kind of psychological evidence for phonemes? Well, phonemes are categorical representations, right? They're categories, and we know category representation is pervasive in psychology, not just for language. We know that there are lots of evidence for category representations. What's the evidence for category representation that we get in linguistics? Well, one way of doing it is to do. So you all are familiar probably with behavioral experiments where you take a T sound and you manipulate the VOT values, the voice sensitive times. You create a continuum of sounds, and then people judge did they hear a V or D or did they hear a T, right? So you present these sounds to the speaker, you manipulate the VOT, and you follow the speaker listeners' judgments about whether they thought they heard a D or a T. When you do that, you typically get so let's say if you have VOT here, the voice onset time from 0 to say 100, and suppose I create a continuum of sounds that goes from D all the way to T. In fact, this is what we did. We used a class synthesizer, and we constructed this stimulus sequence. So this will be a stop alveolar consonant with 0 millisecond VOT. So I release the air at the same time as my vocal cord starts vibrating. This will be the same sound except I have 100 millisecond VOT. So I create a closure. I pump up air into my cavity, I create pressure, and I release the pressure, and 100 milliseconds later, I start vibrating my vocal cord. So I get something like, so here's D, right? The T was something like P, right? So that's the voice onset time difference. So what we can do is we can by using a computer, we then mechanically change the voice onset time in increments of say 5 milliseconds. So we get many sounds. That sounds goes from very D-like to very T-like. If you ask a speaker to behaviorally judge what they heard on many trials of those sounds, and if this axis is the probability of identifying the sound as a T, probability of T perception, I'm going to get a function that kind of looks like this. Right? You don't get a function that looks like this. It's not like you're thinking it sounds more and more T-like the more and more longer the VOT is. It goes from one category to another. Flips between two things. So this kind of behavioral evidence has often been taken as evidence for categorical perception, phoneme perception. However, in a very good paper, Phillips and a bunch of people, they made the argument that, well, these kind of data doesn't really show us anything about abstract phoneme representations, because what you're doing here, you're forced to make choices about phonetic events. So this is really only evidence for phonetic categories. You're listening to the phonetic sounds and you're forced to make a decision. Did I hear a T or did I hear a D? So this is actually only evidence for phonetic categories. So they developed them. So they actually wanted to find some way of getting evidence for abstract phoneme categories that didn't rely on making behavioral classification of phonetic events. And how did they do that? Okay. They did that by, I'm going to tell you quite yet. So I'm going to tell you how they did it, but before I tell you how they did it, I want to explain how we're measuring brain activity. So the way we're going to do this, we're going to measure brain activity without any kind of behavioral task. But I want to explain how we do that first. So here's where we're going. I'm going to show you the experimental method that can sort of tap into phoneme representations rather than phonetic representations. In order to do that, I'm going to give you a mini course in psychophysiology, electrophysiology. Ready? We're going to learn lots of stuff today. So I'm going to explain something called the auditory vocal potential. I'm going to explain memory prediction. I'm going to explain something called the mismatch response. Right. Okay. So how can you look inside the brain? How can you look inside the brain and see how the brain differentiates between, let's say, between two different phonemes, between fully specified phonemes versus partially specified phonemes? How can we get at those mental representations? Okay, so we're going to get at those mental representations by utilizing the brain's automatic responses to speech sounds in general, first of all. Show a picture. So, suppose you are sitting in my lab or anywhere else, and you hear a sound, any kind of sound, whether it's a bird chirping or you hear someone say the word "bah." Right? If I measure, so when you hear the word "bah," there's going to be some response from your brain, from your auditory cortex. There's going to be some electrical activity that is tied to the brain's recognition that you heard a sound. And I can measure that electrical activity, not inside the brain, but outside the brain. So what we're doing is we're putting many electrodes on the surface of your head, and we're measuring, we can measure electrical activity inside the head by looking at voltage changes between 2 points on the surface of the head. So when your neurons are doing something together, they create a current inside the brain, and some of that current propagates to the surface of the head, and you can actually measure that by putting electrodes on top of the head. That's electroencephalography. So what you're looking at here is, you're looking at the head from the top, and all of these little squiggly lines is a single electrode. So what we're looking at now is, so we're looking at, we have time this way, and voltage changes, actually it's microvolt, voltage changes on this axis. So things going like this. Right? It's just like a sound wave, actually. It's the same as a sound wave. And if I put you in my lab, I say the word "bah," and I measure your brain, your head, your surface of your head, and I look at, say, this particular electrode here, I'll see this activity, this electrical activity, this voltage change over time. So this is the point, this is the 0 point, this is when you don't hear anything, and this is where "bah" starts, and this is voltage. It's 0 up until you hear the sound. Once you hear the sound, you see this sort of change in voltage potential over time. And this pattern of voltage change is called the auditory evoked potential. So that's part of your general auditory system. So after about 100 milliseconds, you see a little negative dip in voltage, and then about 200 milliseconds, you see a positive peak, and then it sort of goes back to normal. So that's a measure of your brain's response to speech sounds from the auditory cortex. Auditory cortex is actually on the side, but because of the way current flow, the biggest clearest measurement is actually on top of the head. It depends a little bit on how you measure and how you calculate the voltage differences. But typically, it's sort of measured. So don't get confused about the fact that it's there rather than here, if you know something about brain. Okay, so I actually also want to show you really quickly how do we actually produce this measurement in the lab. So I'll show you, this is how it looks like. So this is how the electrode assembly looks like. And I think I have a sound here, but I don't have to play it. So we put this in people's head, and we play sounds. Sound goes into their ears, and out comes something like this. So this is the raw data that comes out from the system when we measure the brain activity. And this just looks like EEG, right? You all know what EEG looks like. So it's just lots of squiggly lines over time. So it's a lot of data actually. This is so we're sampling every 4 millisecond, and in 3.5 seconds you have 112,000 data points. So it's a lot of data. So you have to find ways to sort of compress and condense and extract information from this data. So this is again, this is the same. This is the view looking at each channel. This is the view from the top of the head. It's the same thing. But you know, the things you can't see any specific. You can't see that nice little auditory potential here, right? That's right. You can't see it because there's a lot of audio activity in the brain going on at the same time. So what I have to do in order to really see the signal in the brain that comes from the auditory perception, I have to do some signal averaging. I have to actually, if I give many trials and I average all of those signals, then whatever is different from trial to trial will average out to 0, and what's constant from every trial will sort of remain the average. So that's how we produce this nice little squiggly line. So here's an example. This is a single subject. That I showed you one trial. This is the same subject with 118 trials. So now you see with 118 trials, you see a little bit of pattern emerging here. It's not just total noise anymore. And if I go from a single subject to 118 trials, here's 35 subjects with 118 trials. So now you're starting to realize, oh my God, you have to really spend a lot of time in the lab to get this really nice data. And that's actually great. So that's what we do. We run many subjects, and we run many trials, and we average all those singles, and then we start to see some pattern coming out. So that's how we produce the auditory potential. So I can't just give you a single bar and then I see exactly this. I have to do a lot of work to produce this little bit. All right, that's methodology. Now let's continue. So suppose now you know what the auditory potential is. All right. Suppose instead of just one single bar, I keep you in my lab and I keep giving the same thing over and over again. Ba, 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 ba. Right? If I do that, your brain will start, okay, I'm getting used to all these bars. In fact, the bar I just heard is just like the previous bar. And also automatically, because I just heard something, I have a memory representation of that sound in my echoic memory, short-term memory. And each time I hear the same sound, something happens. That memory representation gets consolidated. In fact, if you hear the same thing over and over again, that is exactly the function of memory. What is the function of memory? Why do you have memory at all? Huh?
Presumably that.
In general, why do you have to have memory? Well, you need memory in order to predict the future, right? You need memory in order to sort of remember how to go to the bathroom every morning. So it's very, you need to memorize those things to deal with the environment. That's the function of memory. So when I put you in my lab and I do this thing, and you hear many bosses repeatedly, your brain will say, okay, I've heard a lot of boss, I'm going to predict exactly what the next one. The next one's probably going to be a boss as well. Right? That's the function of memory. And in fact, what the brain will do then when I play many bars, ba, 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 the brain will form a memory representation of the ba, it will form a memory representation of the new one, and it will compare those two. And if they're the same, that's exactly what you predicted, right? Then everything's fine. And you put that into the memory representation that you're consolidating. But if I give you a ba, 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 and suddenly I give you a pa, okay, then the pa was not what the brain predicted. The memory system said, oh, I predicted the end of the ba, but I heard a pa, right? And you can actually measure that the brain noticed that something was not as predicted by looking at the auditory evoked potential. Because the auditory evoked potential will change when the thing that you predicted is not the way it was supposed to be. In fact, it looks like this. So the blue line here, that's just a nice little auditory evoked potential like I showed you before. Right? That's the average response to all this ba, 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 ba. But the red line here is how the auditory evoked potential looks like on average when you hear the unexpected, the unpredicted sound, pa. Okay. So if I subtract these two lines from each other, if I subtract these differences, I can plot the difference waveform here. You see it? So this just represents the difference between the blue lines. So this difference here, which happens to go negative because I'm subtracting this from that, is called mismatch negativity response. So the mismatch negativity response is actually not in the brain, but it's a calculated effect. So the mismatch negativity response here is an index of the brain detecting a change in stimulus sequence. And voila, that's what we need. So you can actually produce this measure for any kind of stimulus, any kind of sound stimulus. It's not specific to language. It's a sound specific to sounds. But the nice thing is now is that once you have this measure, you know that this measure comes because there's some kind of featural change into stimuli, right? So I can use this measure to tap into featural changes in phonetic representation or phonemic representation. So here's a picture, by the way, of what's going on. So this is from a paper by Hestvik and this is one sort of standard view of the mismatch negativity response. You have some stimulus coming in here. You have a transient detector system. That's it says N1. That's the first negative bit in the auditory potential that tracks changes in the acoustic information coming into the auditory cortex. And then you also have a feature detector system that maps the incoming stimuli into sensory memory, and then builds a memory representation of these repeating sounds. Right? And then there's a comparison process here that compares the feature analysis of the incoming stimulus with the feature representation of the memory representation of the other sounds. And if those are different, that will generate a mismatch negativity response. So this is the M1 response, the first part of the auditory potential. And you first hear the sound, it's boom, it goes like this, and then you have the sound, same response again, again, again. And then you have this other system that then generates additional activity when you hear a difference between the two sounds. So in the terminology of experimental methodology, these are called the standard stimuli, and this is called the deviant stimulus, or also called the oddball stimulus. So I can map that to my, right, so here you see the auditory evoked potential. The blue line is the N1 is the first thing you repeat there, that tracks the fact that you went from silence to a sound, right? And then the red line, that's the generation of the mismatch response, which changes, which attenuates modulates the auditory potential response. All right, it's good. So now we have, that's what we have. So this is the tool, this is the methodology, this is the tool I now have for tapping into the brain response, brain activity related to different speech sounds. I'm going to use an experiment. Okay. So, are you ready now for the quiz? Tonight. Okay. Any questions so far? Feel free to ask any questions. Yes?
Why 120 electrodes?
Sorry?
Why 120 electrodes?
Why 120? There's no particular reason why 120 electrodes are better than 65 or 32 electrodes. That's the answer to that. So if I know exactly where to measure, I could actually use I could use 2 electrodes. I could put 1 electrode right here, and I can have a little electrode there, and I measure the difference between the 2 of them, and I could just focus on only measuring at this point. The only thing we get is more, of course, we get better spatial resolution. So if you look at people's heads, there's a variability from one person to the other. You know, the response is not going to be exactly in the same place. So if I have better spatial resolution, I can capture more variability and get a better estimate from more subjects. That's one answer. Another answer is that once you do more of this, you might actually find that we found that the mismatch response for D and T, the basic mismatch response for two different phonemes, have actually slightly different spatial distribution. So by having more illustrations, we can capture those. We can avoid a confound that actually the peak of the response is at two different places when we compare them. So yeah, the answer is simply better spatial resolution. All right. So now that you know how to do the auditory work potential, now you know how to do the mismatch negativity experiment. Now we're equipped to do the next thing, which is observe the phoneme. Okay. Now we're going to observe the phoneme. And how are we going to observe the phoneme? That's a big mystery. But that is actually, believe it or not, it's actually amazingly it's possible. All right. So suppose that I give you the ba 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 pa experiment, right? Well, if I do that, I'm going to get a mismatch response to the p, right? But if I give it the exact same ba ba ba, the exact same thing, and then just the p, all I'm really getting a response to is the phonetic difference between those two, right? But this, I know I'm getting a response to the phonetic difference, and in fact, all I need is to identify phonetic differences in order to get a mismatch response. And that's not what the phoneme difference is. Remember, the phonetics is not the same as the phoneme. So if I did that, I'm only tracking your change detection at the phonetic level. So how can I track change detection at the phoneme level? So the phoneme is a more abstract category. They're not the same thing as the signal events, right? And here's how to do that. So the answer how to do that comes from this paper by Phillips and Arild back in 2000. Here's what they did. Okay. So we know that for any given phoneme, there's a lot of phonetic variability within that phoneme, right? And I can actually construct that phonetic variability in the lab, like I did over there. Right? So I can construct a D sound that I can construct many different versions of D by varying the voice onset time. So I can have a D with 0 voice onset time, I can have a D with 60 millisecond voice onset time, and 24 millisecond, 8 millisecond, right? I can give you a huge variability of these. And then I can do the same thing with T, so I can give a different version of the T, right? And this line here, so this is 40 millisecond, 48, 64, 54 millisecond. So in this particular experiment, the threshold between perceiving something as a T versus a D is between 24 and 40 milliseconds. So it's somewhere in there, right? So if you cross the boundary in milliseconds of V of T, all of these guys would be perceived as T, and all of these guys would be perceived as D. So these are the phonetic events, but when you're perceiving them, when you're mapping those to phonemes, you kind of normalize all the differences. And all of these guys are perceived as actually perceived. They're represented as the phoneme D, and all these are represented as the phoneme D. Now, if I vary the standard stimuli in a mismatch negativity experiment, like this, right? If I vary all these standards within category, there's actually not a single phonetic event for each of these standard stimuli. Okay. All different events. But so what do you think happens to the memory representation of all these events? Right? Well, if they're different phonetic events, if I'm going to create, if the brain is trying to create a single memory representation for all of those different phonetic events, what kind of representation could the brain recruit to use as a placeholder for all of those different phonetic events? phonic, yes, exactly. So that was the idea of that was a really good idea that they had. So they did the same type of experiment, but they varied all the standards within category. And yes, you still get a mismatch response to these guys. Actually, they did another part of the experiment was that they added a constant of BOT to all the stimuli, so they shifted half of this over into the other side of the boundary, so you have equally many elements with on this side of the artificial boundary as that side of the artificial boundary, and then they didn't get any mismatch response at all. And that is exactly what's predicted because there isn't any familiar category anymore that can be mapped to half T and half T. So that was actually, so this is a genius paper. They kind of by doing this, they demonstrate that by doing this you can actually get a mismatch response that's indexing, that has a privilege that only indexes phoneme distinctions, not phonetic distinctions. Okay? So the method here is vary the standards in the mismatch side, and then you're going to, if you get a mismatch response, then you're actually getting a mismatch response by the memory system constructing a phoneme representation and then comparing the oddball to that phoneme representation. So this idea was actually, in fact, the idea that you could do this was actually discovered or found out by Arild Lahiri in collaboration with Eulitz, who's a neuroscientist. So they said, okay, let's use this technique as a way to compare very, very abstract feature matrices. So maybe actually I'm going to draw another picture. So, so if I give you many versions of D, D1, D2, D3, right? D. In order to create a single representation of all of those somewhat similar sounds, my brain can recruit my internal mental representation with a phoneme D. Okay, so all of those will be then stored or represented in working memory as the phoneme D. So you're recruiting your ability to represent phonemes as a way to represent all of those events that are slightly different. So I have many Ds. I create a memory representation that utilizes the phoneme, and then I'm going to give you an oddball sound. So I'm going to drawing it as T, but it's only the same sound but with long BOT. So what I hear is actually a phonetic, what I perceive as a phonetic event, right? And then I'm analyzing the features of that, and I'm comparing that to the feature representation that I have in short-term memory. So what I'm doing is I'm comparing a phone to a phoneme representation. Okay. Now, and this is now where the underspecification becomes interesting. Okay, so what we did is, so Eulitz Lahiri, they actually did exactly that, they looked at German vowels actually, where there's a theory that there is a theoretic proposal about which features are underspecified in German vowels, and what they found was evidence for underspecification using vowel stimuli. I'm going to explain their experimental methodology, but using our stimuli. Okay? So we did the same thing with English stops, so we compared D and T, and here you may or may not agree. We assume the theory that says that voicing is underspecified in English, but voicelessness is specified in the phoneme representations. My phonology collaborator has been trying to train me to think of this in terms of spread versus not spread larynx. But I'm so old-fashioned that we're going to use the voicing feature as a cheat sheet. Okay. So don't forget this. Right, so how can we now test this particular theory using the mismatch negative graph? Here's what I'm going to do. So suppose I hear also different T's as my standard stimulus. T, C, top, top, top. Okay, they're varying in VOT. What do? My brain is constructing a memory trace that is recruiting the phoneme as its representation. Okay? So the feature out here is plus specified. Okay. And then I put in an oddball sound, which is the D. Okay, what's the phonetically D is specified as minus spread lines, which gives rise to the perception of voice. But that's a phonetic feature, right? And when I compare that phonetic representation to the phoneme representation of T, this is a direct contradiction feature, right? So there's a feature clash here. So the feature, the system in my auditory cortex that does the feature analysis sees that and knows that, okay, this is a different thing. Something else came into my ear. Okay? You can actually like to think of the comparison. You can think of the comparison process as feature unification from linguistics, right? So if I try to unify minus f with a plus f, I'm going to get a contradiction of features. So that's the way it's formally described. All right, so that means that the brain should notice that those two things are very different. And indeed, it should get a mismatch response. However, suppose I turn the whole thing around. So if I give you many, many Ds as my standard items, there's 5 milliseconds, there's 50 milliseconds, there's 10 milliseconds. Okay, then I'm just the same. I'm going to construct a memory trace. I'm going to recruit my phoneme knowledge or phoneme representation to represent those things, and that's the D. But the D is underspecified, so there's no actually spread or constricted larynx in that feature specification. And now, if I give you the oddball, which is a T, that would be analyzed as having a feature plus spread larynx by your phonetic analysis system. And now, if I compare this feature matrix to this one, what happens? It's like comparing something to nothing, right?
No contrast.
So the contrast is gone, right? Yeah. In fact, if I try to do feature, so unifying the empty set with something, it just gives me the other thing back. So there's no conflict. So now so what do you think the prediction should be for the auditory work potential, for the mismatch negativity?
It shouldn't show up. It shouldn't show up.
It shouldn't. That's correct. The basic prediction is there shouldn't be any mismatch response. And so this is exactly the experimental logic that Eulitz Lahiri invented when they first did this with vowel contrast. So in our study, we decided, okay, let's use this method and test the theory about voicing underspecification, which is what we did. So here again, this is the picture I was going to draw on the blackboard, but the same thing. So phonetic level, at the single oddball stimulus level, we have phonetic representation. At the memory trace representation, we have phonemic representation. So again, when T is compared to D, there is no contrast. When D is compared to T, there is a contrast. So this predicts that there should be an asymmetry or an interaction in terms of whether interaction between mismatch response and which phoneme is a standard versus oddball. So that's it. I'm almost done. I almost spent all my time. So, but I think it's important to explain the sort of the brain basis for the experiments. So it becomes more interesting. So we did 3 experiments where we tested this prediction. In the first experiment, we had subject. So here's one thing. One more thing about the mismatch response. So when you measure the mismatch response, it's actually a highly automatic response. So if I put you, if you're sleeping and I put those sounds into your ear, your brain will still respond. In fact, if you're in a coma, people actually use the mismatch response to determine whether someone who is comatose still has enough brain functioning for it to warrant, say, surgery or say, resuscitation, for example. So you can actually run this experiment on comatose patients and see if the auditory cortex still distinguishes between 2 sounds. So that means that the brain is still working, right? So it's highly automatic. So we did an experiment where we actually had the subjects not pay attention to the sound at all. We had the subjects simply watch a silent movie. So we said, just watch this movie and just ignore the things coming into your ear while But we actually ran the experiment first by turning the subject's attention to the stimuli. Actually for reasons that's orthogonal to the study, we were interested in running this experiment with kids and language between kids that has some attention deficit disorder. So we wanted to manipulate the attentional orientation towards the stimuli versus not attending to the stimuli. So that's for different reasons. Now I'm going to show you both experiments anyway. So we ran these two experiments. These are typical mismatch negativity experiments. One we had them pay attention to the stimuli, one we had them pay attention away from the stimuli. So if the response is highly automatic, it should show up in both conditions. This also allowed us to sort of test whether the phonological differences, are they also automatic or they depend on attention. And then I'm going to explain the third experiment in a little bit. So let me just give you the results from those first two experiments. So we ran, we had 24 subjects. We actually reconstructed the stimuli that were so they were exactly the same as in Colin, Phillips, Oz paper, and we used exactly the same experimental methodology. So we replicated exactly the study from there. Let me skip that one. Okay, so here's what we found. So there's when we did the experiment, and actually for all experiments, we actually observed two types of ERP components. We observed the mismatch negativity component, mismatch negativity response, and we also observe a later brain response. That's called late discriminatory negativity. So I'll tell you about both of them and what they mean. So let's see. First show you the mismatch response. So here's the result from the first experiment. Let's just look at these two lines, because I don't have time to explain this. It's just another way of actually generating the measure using different type of analysis method. So, and I can explain that if there's questions about it. But let's just look at this. So here is the results when we ran the experiment with D as an oddball. I have to actually say one thing. When we're doing this experiment, we're actually running them 2 times, one with D as an oddball and T as a standard. And then we switch it around, we put T as an the other way around, right? So that each phoneme is functioning both as a standard and as an oddball. Now, there could be inherent differences in here. There are inherent differences between T and D that themselves could give rise to slight differences in brain response, especially with respect to the latency and amplitude of the electrical response. So what you really want to do is you want to control for any inherent differences between these between the sounds to make sure that the mismatch response you're getting is only due to mismatch, not due to physical differences between the speech sounds. In fact, I'll show you one thing. Yeah. This one, right? If I measure the auditory work potential to say only the standards, to say only D, only T, and then map, and then plot the brain response to those sounds. Here is the brain response to D, and here's the brain response to T. You see there's actually about a 60 millisecond difference in the latency of the peak of the response to the two speech sounds, to the two sets of sounds. And that difference actually corresponds almost to the average difference between the V and T value in the stimuli. So we know that the inherent response from the brain to a D is going to be a little bit different from T in terms of latency. It looks like there's a little amplitude difference, but that was not significant. But this difference is meaningful, right? So if this was a single D, if this was a set of standard Ds, and this was a single T, if I subtract these two from each other, I'm going to get a difference here already, right? But that difference is actually just due to the latency difference between the brain's response to the two sounds, due to the DOT difference. So therefore, what we do is we first construct a waveform for D when it's an oddball standard, and then we take the data from another part of the experiment where the D is the oddball, and then we subtract them from each other. So D is its own control. Right. So that's where you control for that potential compound. So that's why it says D here is standard D, and then red here is deviant D. So you see when D is, so we get a big mismatch response for D here. Right, so this is a standard, this is deviant, difference here is the gradient. So this is a significant difference. Here's the difference for T. So actually we didn't get a mismatch response for missing there? Wow. It seems like it's working. The data seems to bear out the predictions. We also looked at something called the late discriminatory negativity. So that's the brain response that takes place later in time. So you see here, the red line is different from the blue line. And actually, that response is more frontal to the motor over here. So that response is believed to be tied to a difference between two stimuli, so rising to the level of awareness in the cognitive system. So now we're going from automatic detection of differences to a difference that the subject kind of notices at the conscious level. And that's also why it's related in time. So the early responses are highly automatic, below level consciousness. The later responses are related to more higher level cognitive processes. So actually, we observe the same distinction also in the late part of the response. Okay. Now let me skip forward to right. So it looks like underspecification wipes out the contrast in the mismatch response. Now you might ask yourself, does that mean that people can't hear the difference between D and T? That would be, obviously cannot be the case, right? Because you can still hear the difference between D and T. So we think, our take on this is that the fact you can hear the difference between D and T in regular speech, or even in the experiment, if I ask you to pay attention, is because you still represent and track the phonetic differences. So you have a phonetic difference as well as a phonemic difference that you should see. But the mismatch response here only tracks the phonemic difference. Okay, so in experiment 2, let me just quickly go to experiment 2. It's the same experiment, except it now had subjects watch a movie, sound movie. So again, you see there's a mismatch response for D, and actually here, the lines looks like they're flipped. The mismatch, the oddball actually has a higher amplitude than the standard. So it looks like it's kind of flipped in polarity. But actually, this is not significant, so it's not meaningful. So basically what this means is we get the same effect whether you pay attention to the stimuli or whether you pay attention to something else. So it's an automatic response. The phoneme differences. Phoneme actually changes automatically. Okay, so now we're actually at the same place where Aditi, Lahiri, and Eulitz sort of stopped their research. They found the same contrast for German vowel contrast, and they made similar conclusions. Okay, this is evidence for underspecification. We decided to go one step further, to push the theory a little bit more. And here's how we did that. So remember the whole logic of the experiment, that is that I'm varying the standards so that I create a phoneme representation. Right? Okay, so what would happen if I didn't vary the standards? What would be the memory representation? The phonetic, exactly. Now if I have a phonetic memory trace for the standard, and then I have an oddball that's also phonetic, what would happen to the contrast there depending on D versus T? What would be the prediction now? Yes, exactly. So, spoiler. That's right. So if I instead of varying the D's, I have the same D all the time, and then I have single oddball T, and then I switch it around, I have the same T's as a standard and the single oddball D. Now, if I don't vary them at all, then the memory trace could be the phonetic representation. And you think it will be the phonetic representation because you don't need to recruit any more representational resources than is necessary. And now there's going to be full contrast in both directions. So now we predict that you should get that the mismatch for T should come back again. So that's the last experiment we did. Okay. And actually, we also did this experiment for another reason. Can I talk for a little bit more?
We're chasing us up.
Okay. And you guys are not falling asleep yet? Okay. So these kind of asymmetries have actually been observed. Actually, even in Colin Moran's Phillips paper, they actually noticed that there was a difference between D and T, but they didn't say, well, no, why. most sort of sensible reaction, right, is to say, well, there's got to be some inherent difference between these speech sounds that causes the brain to respond differently, right? That would be the first thing you would look for. So, for instance, there could be, notice that D has short VOT and T has very long VOT. And in fact, if you think about it, the D, when you have long VOT, you kind of have more things going on acoustically, phonetically, right? You have the closure is clearly separated from the onset of voicing, right? But when you have voice sounds, the release of the air and the onset of voicing kind of simultaneous. So people have said that, well, in a sense, there's one acoustic event, one articulatory acoustic event in voice consonants, whereas there's two events in voiceless consonants. So maybe that's 1 versus 2 itself is simply what is the source of this mismatch asymmetry. Indeed, people like people who studied the measured actually electrical responses from neurons inside the head. So they open up the head and they place electrodes directly on specific areas of the brain and measure single or multiple neurons directly. And actually, this is a guy called Steinschneider from City College in New York. So they're doing this experiment with monkeys. Okay? So they take a monkey and they open the brain with electrodes and they measure how these specific neurons respond differentially to changes in voice onset time. Okay. And what they found was, so these are just the stimuli they used. So they used 4 different stimuli, 0, 20, 40, 60, and this is about between these. This is where the threshold boundary is for humans. Okay, so let me explain this. So when they're looking at single neuron or small set of neurons and the response to sounds in these neurons in order to cortex, they found that when you have 0 millisecond VOT, you get a single sort of spike voltage change in these neurons. This spike up here is the response from I forget whether it's single neurons or small or a set of neurons. Now, when you have the long VOT stimuli, that is, we have release of air followed by onset of voicing, you actually get 2 separate responses. You get multiple responses. You get the one response right at the release of air, and then you get a separate response for the onset of voicing. Right? And the same thing for 60, and the same thing for 40, and it sort of decreases after the threshold. Okay, so what does this mean? And this monkey's brains and the auditory cortex is extremely similar to the human auditory cortex. So what this suggests is that neurons in auditory cortex are kind of tuned, specific neurons are tuned to respond differently to short versus long VOT stimuli. Okay. So then you might very reasonably say that, well, if you observe a mismatch, it's an asymmetry, a mismatch response to D versus T, that could actually come from this fact that the actual neural response is inherently different. Although you sort of have to work out how this particular single neuron response materializes as a difference in the eventual potential, which is an average response from many trials. It's slightly different in nature. Now, if this was true though, if the difference between D and T as an oddball comes from this difference in neural response patterns, then it should make a difference whether I vary the standard. It should not matter whether I present a single D or many different Ds. Right? So if this is a source of difference, it shouldn't matter. So by changing,
yes, by varying only voice onset time and keeping the rest of your stimuli same, you are introducing phonetic unreality because with real speech, there's not just a difference in VOT, voice onset time, between T and D in, say, English. There's also a huge difference in amplitude. The T in English, say, onset T, onset to a stressed vowel, has a very strong amplitude noise component, which you didn't manipulate at all, did you?
No.
No. So you're manipulating only one of the two important cues for an English speaker or hearer. Now, if you're working with Russian, of course, we're into a different game altogether. You don't have that huge difference in amplitude of the, and you were talking about inflating yourself for the T. Yeah, exactly. You inflate yourself, and you inflate the cavity, and then when that air is released, it produces a strong noise source, which obviously an English speaker and hearer is going to use. And you know, with your results on the board here, from these are from direct tapping of the brain. Right?
Yeah.
You can see clearly that the strong noise source associated with T, with voiceless stops in English, shows up very clearly, and you notice that it's extremely strong, the reaction to the noise source on the voiceless stops. Extremely strong.
Here?
It's your first, no, your first reaction here, you see, is to the noise source, and if the VOT delay is long enough, you're going to get a distinct peak for the voice onset.
Yes.
So here, the auditory system is responding to the noise burst. And if you take a piece of paper, you can even see it by holding a piece of paper in front of the English speaker. And when they say ta, 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 you see the paper move. But when they say ba, 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 you don't see the paper move because there's no strong noise source. So this strong noise source, it's the reaction to it, the brain's reaction to it, is stronger than the VOT response here. So in fact, with these two cues for voiceless stops in English, you've been manipulating only the weaker one, which is the voice onset time. You've not been manipulating the stronger one, which is the noise source.
Yeah, that's right. Actually, these are the stimuli that generate those responses are exact. They're only varied. It wasn't nothing else. That's
yeah, nothing else. Yeah,
that's right. No, you're right. I mean,
so your stimuli were phonetically unreal from the point of view of English.
Absolutely. So all these stimuli are highly artificial. That's true.
Yeah.
And the reason we're doing that is that if we don't do that, it becomes very difficult.
Oh,
to,
yeah, of course.
To find out where the stimuli effect is a sort of my effect, right? So that's true. We do the stimuli are not realistic.
Not phonetically.
Natural in that sense.
Phonetically natural.
However, still, if I use the stimuli and I said dog versus dog, people will still perceive that as two different tones, two different words. So perceptually, it still taps into people's long-term memory representations for the stimuli. So
yeah. I mean, your subjects have to work with the stimuli that you give them.
Yeah.
Oh, yeah. They've got nothing else to work.
That's true. But this is true for everything in experimental psychology. So if you look at vision research, look at the stimuli they use in research on the visual system, they're always highly artificial, where they just sort of try to manipulate only one thing and keep everything else constant. So it's sort of like, it's the easiest way to get a good measure from the brain.
Yeah, and
We should probably move to the last experiment.
Yeah, but you're absolutely right.
yeah, and for my PhD, I was working with Russian and Egyptian Arabic speakers on some of these features, and to my amazement, English speakers had much less trouble perceiving Russian palatalization, which is supposed to be exotic for an English speaker. They had much less trouble perceiving that Russian distinction based on palatalization than they did Russian voicing. They didn't know what to do. They didn't know how to perceive Russian voicing because it's so totally different from the voice contrast in Russian is so totally different from the one in English. Because Russian, for Russian onset stops that are voiced, they're actually pre-voiced. So the voicing begins here somewhere, you know, before the release. Whereas in English, it's simultaneous or a little after. And English speakers were they just didn't know how to perceive Russian minimal pairs based on
although they could probably be trained to it if they don't know.
Oh yes, of course, yeah. But they found it confusing because the VOT and the amplitude of the noise so totally different.
Yeah.
And of course, it produced mismatches in their mind because they wanted to hear a late VOT and they wanted to hear that high amplitude noise, and it wasn't there. Neither of the two cues was present in the Russian for them.
But so what we're hoping is that even though we use highly constrained stimuli, that the finding will generalize to the whole range of possible phonetic distinction. But let me just show you what the let me just get back to my experiment. So
yeah.
So here are the results though, by the way. So when we didn't vary the standards, the brain actually gives a sort of full-blown mismatch response to both the D and the T. That was really different. So here's the green line, here's the mismatch response to D when we don't vary the standards, and the black line here is the mismatch response to T when we don't vary the standards. So that's kind of if you expect, even if this is true, that cannot be the source of the asymmetry, because when we don't vary the standards, we get a mismatch response in both cases, whether it has the single spike or the double spike. So the single spike versus the double spike can't be the source for the asymmetry that we observe in other experiments. Yes.
I was just wondering, your non-varying stimuli.
Yes.
Did they have the same average VOT of your varying?
Actually, just a single VOT value.
Right. Yeah. But that single value, was it the average of the varying values? So
yeah, actually, it was. Yeah, we did pick the one that was in the middle of the range that we used in the other case. Yeah, so we took actually empirically we also ran a behavioral test for all the subjects we ran, and so the 40 millisecond was the mean threshold for all the subjects. So we picked from the, so here's the range where everybody thought there was a D, and we picked the middle for that, and the middle. Right. So they were sort of like very prototypical in that sense. Yeah, we could actually, we could also have an experiment where we actually tried multiple versions of the Ds and make sure that it wasn't just an artifactual result of that particular VOT.
Well, exactly. So if your variable stimuli had less of a distance between their average and the average of the oddball, you might claim that it was a phonetic effect. But the average distance in VOT is the same in both versions, then the average phonetic difference was equal. So you could say, okay, it's not phonetic effect.
Well, no matter, so by our logic, no matter which single VOT value you pick from the D range and the T range, if we present just the same sound over and over again, we would argue that you only get a phonetic mismatch. So it shouldn't matter which one we picked. So if we did pick different ones and it did matter, then we're wrong. That's right. Then we were wrong. So that's the end of the story. So let me summarize. Right. So when you use the paradigm, then of course it's formation of phonetic parametrace. MMN appear for both phonics, and when you're using the paradigm encourage formation of phonemic parametrace, MMNs only appears for underspecified. So in summary then, as you were, I'm just repeating what you